So, hello everybody. My name is Harald Yndestad, and I'm professor at the University of Trondheim, a professor in cybernetics. And my talk today is, I raised the question, is the climate variability deterministic or not? Is this deterministic like a clock? This is a research question I have been working on for the last 20 years, and I'm still working on it. But at the moment, I'm working on a framework of this question. I will start with Francis Bacon, one of my heroes. And he said, the motive of science is to predict the future, to control the future. But is the future deterministic? If not, we can only explain the past. It's so simple. This means that no computers in the world can predict the future if they are not building in something deterministic in the data. And if we cannot predict the future, we cannot control the future. For example, the climate variability. And my background is cybernetics. I study cybernetics is a control theory for many years, and also signal theory. Signal theories is to understand time series. Is there something deterministic in the time series or only noise? Cybernetics is to compress the noise and to keep the informations. So there is linked the two aspects of the same. In 1990s, I started to work on this topic. The lunar or the tide influences the climate, and the climate influences the ecosystem. And I work on other things for a while, and in 1914 I started to work on solar variability, and at the last 2 years I've been working on global climate variability. So I will try to explain for you my story about this research. This is a picture from my hometown, Ålesund in Norway, at the west coast, the biggest fishing town in Norway. The picture for 1960, everybody was happy because there was so much fishery, and the fishery was fish was crowding everywhere, and everybody got rich for fishing. But suddenly the fish disappeared, and everybody got unhappy. And who is to blame? Was it the fisherman who has overfished and taken all the fish? Well, the fishermen, they blame the marine scientists. They have not been able to compute the future stock of cod. So everybody was angry, and it boiled down to, can we predict the future of the biomass? In 1990s, the fisher industry, they come to me and they said, well, Harald, can you predict the future of stock the next 10 years? Oh, I said, this is $1 million question. Well, I said, I can give it a try. It's a point there. So what I did is I take on my, this is actually the same slide from a spreadsheet from 1960s. I plotted in the biomass of cod, and here is the collapse of cod, and here is the collapse situation in the 1970s, 80s, and here is it started to grow. So the first thing I did, it was done in only 20 minutes. I computed the autocorrelation, and the autocorrelation said that, oh, sorry, autocorrelation say we can compute only 1 year in the future, maybe 2. So they was not very happy what they heard, because they have big investment of expensive controllers. But I said, there is something funny here. There is a 6-year cycle. It shouldn't be there. For the Venus spectrum, say that there shouldn't be a cycle here. So if is this a stationary cycle or is a random cycle? Or to be a stationary cycle, it's not enough to have on the autocorrelation, it must have a stationary source. So is it something deterministic outside the biomass? So this was the start of it all, my pain. The next step was, where it could be the stationary period. Well, go back. Here is the inflow on North Atlantic water. Between Scotland and Faroe. And the North Atlantic water flows out on the Norwegian coastline and up in the Barents Sea and up in the Arctic Ocean and go back and down at the cool stream at the Greenland coast here. So this has been known for 100 years. It was Otto Pettersson, the Swedish oceanographer, who started to monitor this data series at 1800. And now it is the longest oceanographic data series in the world. And what it says is that the temperature has increased from 1800 up to 1940. So here is a warm period. And then it started to decline. It got into a cold period. And here was the biomass collapse. So I said to the fishermen, well, you are not the only overfishing. The nature has something to do with it. It collapsed when the biomass was at the minimum. So it was declining all the time when the temperature was decreases. So, but here it started to grow, and this is why the biomass in the Barents Sea are growing. And so back to the Francis Bacon. Is this deterministic or no? If it's random, we cannot compute the future. After a lot of work, I identified a spectrum in this data series. No. I found out here is the lunar tide, 18.6-year cycles. And the red one here is the temperature. It was a 18.6-year cycle in a mean, and it had a 30 degrees delay. And this mean temperature here was a 4th subharmonic. You are all from the energy knows the frequencies. What is the frequencies? And it was a maximum here in 1940 when the short periods of 18.6 years had the maximum and the 74 years period had a maximum. And there was a minimum when the 74-year period had a minimum there. So I said to the fisherman, if you know the clock, Your investment when the clock is racing, you will always earn money. But if you invest here, you will always lose money. What this says is that there is deterministic periods in the sea temperature. And when there are deterministic periods in the sea temperature, it's a deterministic, not only the ecosystem, but the whole climate. So the whole climate, not only in Scandinavia, but in North Europe, is dependent on this stationary period. So the climate, the last 100 years, has been controlled by the moon. So if somebody tries to control the climate, they have to stop the moon. There is deterministic periods. But there is more to this story. Here is a fisherman. But this has been known for others for years. So who has been so clever? Yes, the cod. The cod has been much cleverer than us. The cod had known this for thousands of years. So this clever cod, he has solved an optimization problem without knowing mathematics. So he have found out that if he investment in recruit 3 times in a period of 16.6 years, he will always it will solve the optimum recruitment. So here is a 6 temperature cycle, and this cod, when he recruit in the warm period, 2 times when the warm periods, or 1 time in the cold periods. And in the warm period, he had recruit 20 times more than in the cold periods. So the period of cod is the recruitment of the cod is period and phase locked to the lunar nodal tide. Fantastic. And the sum of this recruitment influenced a biomass of 18.6 years. So to be a professor and learn from mathematics is one thing, but you can learn even more by learning from nature. Here is a slide that I will show the importance of the phase information. Many today have talked about the periods, but to me, the phase information is everything. It's very important to know the phase information, because the phases tell us when the events are happening. Here is the start. Here is it starts with the Earth axis. The lunar nodal tide is caused by a 3-body problem between the Earth and the Moon and the Sun. So because of this 3-body problem, the Earth axis is wobbling at about 5 arc degrees in a period of 18.6 years. It's called the Earth rotation. When the Earth are wobbling, it causes a lunar nodal tide, which is a standing wave between equator and Arctic. And when you have a standing wave there, you have an amplitude variations, not much, it's only 4 or 5 centimeters, but there are also a current. So it's a current wave and an amplitude wave. And from the current wave and amplitude wave, you get the circulations. And from this circulation, there will be a mixing between temperature layers in the Gulf Stream. And this is the explanation for the temperature fluctuation of 18.6 degrees. And this tide has a phase delay of 90 degrees related to the Earth axis. And the temperature have also a phase delay of 90 degrees from this lunar tide. And when the currents are coming up to the Arctic, it influences the Arctic ice extent by a period of 18.6 years. And when it influences the Arctic ice extent, it influences the now index. When it influences the now index, it influences the weather. And when it influences the weather, it influences the rainfall and the economy for all those working on electricity problems. You see, everything are connected. Here is a slide from I worked on for some time, the North Atlantic oscillations. The now index is the pressure difference between Iceland and Ålesund. So this air pressure difference, it controls the weather in the whole Scandinavia, and I also think in the North Europe. And how much rainfall, stormy weather, cold winter, warm and wet winter, and so on. So it's very important indicators of the weather. Here is a data series of the now index from 1822. It looks very random. But after a wavelength spectrum analysis, you see that there are long fluctuations. And these long fluctuations are related to this 64 years period, fourth harmonic from the lunar nodal tide. And there also are a lunar nodal period. So this weather, changes in the weather, are controlled also by the moon. You see here in 1960s, it was at a low level. It's a cold period. It was very cold in Norway, where I was a kid. And here is a warm period here. And you see that the now index is turning. Here another, I have a cooperation with Pinner Institute in Murmansk, and I got this data series from them. It shows the same, the difference between this data series from between Scotland and Faroe is a delay of about 3 years. So it's a delay, or current delay, of about 3 years from Scotland up to the Barents Sea. And here is a growing temperature, so it's a cold period, work up to a warm period, and goes to the cold period. Here was the biomass collapse. What I did is to compute the wavelength spectrum of this, and I found that this data series is controlled by the lunar nodal periods. The lunar nodal periods are stationary. And when I know these lunar nodal periods are stationary, I can make a cybernetic models. And when I have a cybernetic models, I can compute a new longer data series. And I have this longer data series, I can take a wavelength spectrum analyze this new data series. And here is the results. It shows here the cold period. Here is the warmer period. So here is the warm period. Here everybody was happy, much cod. And here it goes to a colder period, and here the biomass collapsed. And from this long period here, come a new warm period again. So here we are now, at the top. So at the moment, we are at the top, and this is turning into a colder period. So I believe that the fishermen won't be happy the next 30 years. The biomass will collapse again. And many will be, it will be a new cold period. Arctic ice is coming back. And people living in the coast of Norway will not be happy. So this is a very challenge for the future, I think. So this is here is another example. When I took my PhD in 2004, the PhD committee come from a conference, an IPC conference in Iceland. And they was very excited because they have heard that the Arctic temperature will increase between 5 and 7 degrees the next 100 years. And I got this next $1 million question again. What will be the influence on the ecosystem in the Barents Sea when this temperature will increase 5 degrees in the Arctic? And I had 2 weeks to solve the problems. What I did, I contacted Copenhagen University, and I got this data series of temperature on Greenland from 500 after death, and plotted on my MATLAB, and it looked very noisy. So I took a wavelength spectrum analysis of this data series. I saw, aha, here is something interesting. Here is a long wave. And when I dig deeper into this data, I found that there was a stationary period of about 186 years. And this stationary period here, you had a minimum in the 18th century, which had a coincidence to Arctic ice, which I also have analyzed in my PhD. And here it started to grow up here. And I conclude that if this is a stationary period, it expected to have a turning point and a new minimum at about 2040. And also a second period that showed a deep minimum at 2105. So this told me that if I follow the data and not the doctrines, we may expect a new cold period. So I said in my thesis presentation, sorry, my data say there is no 5 to 7 degrees in Arctic the next 100 years. What did this data tell me is that we are moving into a deep cold period. A deep cold period comparable to what we have in the 14th century. And this will lead to a collapse in the biomass. I passed the test, so I got my PhD. Well, this was the data told me. So I started to wondering again. Well, I speculated in 10 years. 10 years I speculated. Well, what is the source of this 118 6 years data. It must have a source. I saw it is stationary in the data set from Greenland, but what is the source? What can be the source? So I decided, before I become too old, to dig for it. And I started with the Francis Bacon again. And I started with a research question. Has the solar irradiation stationary periods? If not, we can never predict the future solar irradiation. But if so, the periods must have an external source as the first cause. Because if it has not influence for external cause, because the sun by itself cannot produce stationary periods. If you have an autonomous system, this is known from cybernetics, it will only produce a random periods. It cannot produce a stationary period. So if there is a stationary period, it would come from somewhere outside the sun. So I called it, there must be a first cause, a cause of causes. This is what I learned from Aristotle. Lucky, I got this data series from Scafetta. Scafetta and Wilson, they produced this data series of total solar irradiations. And it shows some fluctuations. So it told me this solar is not constant. There are a variability in the sun. So I took a new wavelet spectrum analysis and computed the autocorrelation of the total spectrum, and I saw something interesting. The first peak here was at the 11-year peak, and there was a peak at the 29-year and the 84-year, and here was 186. So this autocorrelation had the fingerprints of the large planets. So this was the cause of causes. The radiation for the sun had the fingerprints from the large planet. So this tells me that there is also a solar clock, not only a lunar clock, there is a solar clock. Controlled by the Saturn, Jupiter, Uranus, and Neptune. But it's not enough to have the periods. You have it's as well important to have the phase informations. So I decided that I use the perihelion as a reference for the phase. So that now I could produce a spectrum and I can make models. And I used the I looked at how does this influence the barycenters. The barycenters of the sun is known. Here is the oscillation of the barycenters. It looks random. If you here's the barycenter in the y and x axis. So when you look on the barycenter, it looks random. But when I analyze this data series, I saw that the barycenter also have the fingerprints of the large planets. So there was a direct relation between solar position oscillation, the planet's position oscillation, and the solar position oscillation. So this is a Newtoner response. It's caused by gravity. The next step was to step over to the total solar irradiations. When the sun is wobbling, controlled by the large planet, you are also wobbling the solar plasma and the solar dynamic. How this is happening inside the sun is not well known. But what I estimated in my data is that, and I believe this is Maxwell who is responsible for this transform from the solar position oscillation into the solar irradiation. But the data said there is a very close relation between solar position oscillation and the total solar irradiation, but they had opposite phase. When you know the periods and the phase, you can make a model, a cybernetic model. So first, here is a simplified model, a model of total solar irradiation based on the influence from Uranus and Neptune. And this shows how the fluctuation of these models from 2000 before Christ to 3000 after death. What is interesting here is that this is a period of about 4,000 years. 4,000 years. And they had a maximum at about 500 before Christ. And a minimum here at the 15th century, which all of you, or most of you know, it was a little ice age. This means that we are a recovery period at the moment of climate. Recovery takes more than 1,000 years more. You see? And this rapid oscillation here, I found out this happens 178 years with each user period. And this period here was that I identified in the Greenland data series. So now I know the source of this Greenland oscillation. Here is results of solar clock when I compute from Saturn, Uranus, and Neptune, and from 1,000 and up to 2,200. What is interesting, there is a coincidence to the value known Oort period. Here, this cold period. Here is a Wolf minimum, the Spörer minimum, the Maunder minimum, the Delta minimum, and the next minimum. So this means there is a deep minimum coincidence known to known solar periods from Ususkin period. And the next deep minimum is at about 2060. Not far away from 2040, I predicted. So how this influenced on the known data series, temperature data series on Earth. This is a very known global data series, Headcrut 4, from 1840 to 2017. The yellow here is the land temperature. It shows that it is colder than the mean temperature. The blue is a mean temperature, and the red is a sea surface temperature. So it's colder in the cold period on land and warmer in the warm period on land. And why? Because the sea is have an accumulation of heat. So if we go back to my hero, Francis Bacon, can we predict the future over here? Well, we can take a Newton approach, which has been done by IPCC. What they did, they found the growth rate here, mean growth rate here, and then they predicted how this will grow up to the next 100 years. So when you use the Newton approach, everybody knows from system dynamics is that everything is growing to infinity or declining into zero. They are not able to identify the turning point. So to identify a turning point, you have to know the spectrum. So this is another approach to compute the spectrum. You have to know the spectrum to compute the turning point. So that's what I did. I computed the spectrum. Here is a wavelet spectrum. What is interesting is that this wavelet spectrum is period and phase-locked to the solar-lunar periods. These mathematic models I made from the planets. And the difference, phase difference, is less than 5 years. It's incredible. And the difference between when I take the spectrum and correlate it to the original data series, the correlation is 91. This means only 10% of the variability I can't account for in the solar-lunar spectrum. When I have the stationary periods and I have the phase information, I can make a model of global temperature. And when I have a global temperature model, I can produce a new data series. And here is the results. Computed results from 1000 AD up to 2200 AD. And it shows remarkable that there's a minimum at the Oort, at the Wolf, at the Spurrer, at the Maunder, the Delta, and the next. And it's phase-locked to the solar periods. And the minimum temperature is now at 2090. So there is a time lag from the minimum of solar minimum to the lunar to the global temperature. And the reason there is a time lag is the accumulation of heat in oceans. So from this model, we can expect a new minimum, a Maunder type minimum at about 2090. So how about longer data series? This is a Greenland temperature known as a GISP2, which is also a very well-known data series. How much? And it shows that, and it looks random, but it shows, if you analyze this, it shows that various period spectrum, it's a stationary spectrum, And it's a period of about 420 years. And the modern warm period is from 1840 to 2050. And the cold period from 2050 to 2160, and a deep minimum at 2100. Here is a wavelength power spectrum from over 4,000 years. It shows there as a stationary period of 2,406 years, known as the Hallstatt periods. Here is a cold, here is a warm, cold, warm. It had the minimum at 2013. There is a delay from the sea temperature to Greenland because the Greenland temperature influences the temperature in the oceans. So there is a 90-degree phase lag from the ocean temperature to the Greenland temperature variability. Here we see all the periods. First I compute the wavelength spectrum, then I compute the Hilbert transform, and compute all the phase informations. So here is the long periods, here is shorter periods, even shorter periods. So this is a map of the climate variability. What is interesting here, that all these maps from here and up here has a period and phase locked to the solar nodal periods. This means that these periods are deterministic, but not controllable. You cannot control these periods. They are coming. How much time again? Overtime, yeah. Well, what I'm trying to say here is that there is a coincidence between different data series, the global temperature, solar temperature, and so on. And here is a minimum from the sunspots, and they show essentially the same. So, the last slide. This is a glacier not far away from where I live. And this is decreasing the last 100 years. But I believe it's coming back. And the winter is coming. Thank you.